Yes, good evening everyone. Welcome to ACE Online. So today we are going to see some questions related to electrical machines in the score booster series here. Now here I'm going to discuss NAT and MSQ, some of the important questions, how we get the questions in actual examination. Let's see first one. See the question. Which of the following are correct regarding voltage regulation of transformer? See, for every question I will give some time, 1 or 2 minutes time. First you try to solve quickly and then later cross verify what is the answers you are getting. Okay. Now first see here, first option is it can be calculated at any load and power factor regulation. Second, it depends on the voltage to be applied during short circuit test. Third, it has zero regulation in leading power factor. It has zero regulation in the leading power factor near to where it is. Check. Near to zero power factor. Zero regulation near to zero power factor. And fourth option is if maximum value of regulation increase, then its power factor also increase. Now first you try to answer which are correct here. Tell me. See. First option is there here, it can be calculated at any load and power factor. Yes, this is correct only. That is, regulation we can define not only at full load. Generally in definition we take no load to full load to the full load condition. Not only there, because every time we don't apply full load on the transformer, it may be half load, it may be 70-80% like that. So anywhere we can calculate. And also any power factor we can calculate. Means different loads, different power factors will be there. So this is correct one. It depends on the voltage to be applied during short circuit test. Yes. See, we need to apply some voltage during short circuit test. How much voltage we need to apply? We no need to apply rated voltage. We have to apply some reduced voltage. Some reduced voltage we need to apply. But how much it is? That is approximately some percentage we have. Okay. So if that voltage required to be applied is more, then automatically impedance value increase. For the same rated current, if voltage required is more, impedance increases. So like that, it depends on the voltage to be applied during short circuit test. If you apply more voltage, we get more regulation. If you apply less voltage, means for the transformer having higher voltages at rated current, they will have more regulation. Okay, so it depends on the voltage to be applied during short circuit test. Third, it has zero regulation in leading power factor near to zero. This is wrong. So zero regulation in leading, that is okay. But where we get zero regulation always near to 1 UPF we get, not 0. If maximum value of regulation increase, then its power factor also increase. See, maximum value of regulation. If you remember, what is the maximum value of regulation? Percentage Z itself maximum regulation per unit impedance or percentage impedance. That is the maximum. If this value increases, then what is the power factor? So we know power factor is what? Always according to impedance parameters R divided by Z only. No? Whenever Z value increase, what is the power factor? Generally decrease. But what is the statement? If maximum value of regulation increase, then its power factor also increase. So this is wrong. Power factor decreases. Okay. So which are correct here? So first A and B are correct here. A and B are correct. Next question. See this question. A three-phase delta star transformer with a turns ratio of 2.5 supplying a load of 14 kilowatt at 440 volt 0.866 lagging power factor. Calculate its primary current taken from supply. See, in this type of three-phase questions, we should be take care like whether they are asking phase current or they are asking line current. Okay, first you try yourself. So 1 minute time to you. So try it. And later I will do the answer here. So it should be clear what they are asking here, whether they are asking phase current or they are asking line current. Here it is just I asked current taken from supply is dash transformer. Which transformer connection it is? Delta star. Delta star. Then what is the current taken from supply means nothing but line current. So primary side line current we have to calculate. Okay. So in this type of calculations now you should every time cross check whether you calculated phase or line value or they are asking which value. So and which value you are providing, because in numerical answer type of questions you should be take care like anything. Before writing that answer there you should observe what they are asking in three phase case particularly. Whether it is line R phase. Okay, what is your answer? Cross check it is. Okay, let's see. See here. It is supplying how much load? 14 kilowatt at 440 volt, 0.866. So with that voltage available, secondary side current we can find. What is the secondary current? Line current equal to power divided by 14K, calculate this, divided by root 3, the line voltage given 440 on secondary and power factor 0.866. Calculate this, how much current we get? The current I2. So it is coming 21.21. Cross check these values, everyone. This is line current and also phase current, because secondary star connection, no? Phase current also same it is. So this is only phase current, line current, both. Now we need primary side line current. First let us calculate primary phase current here. Then according to current ratio, I1 phase upon I2 phase equal to N2 by N1, transformation ratio it is, N2 by N1. But given here turns ratio 2.5. Turns ratio is N1 by N2, then what is N2 by N1? 1 divided by 2.5 it is. Simplify this, I1 phase equals to how much we get? This is 21.21 divided by 2.5. It is coming 8.48. But if you write this one as the answer directly, that will be wrong again, because they are asking current taken from supply, which is line current it is. Therefore, and primary, which connection is there? Delta, no? Then what is the primary line current? Root 3 times of this, 8.48. How much it is? It is coming line current 14.69 ampere. Okay, you will have 14.6 to 14.7 amps, like that some range will be there. Right now the answer is 14.69. All of you cross check these values. Okay, next question. Next series question. A 800 volt by 600 volt auto transformer supplying a resistive load of 6 ohm at LV side. Calculate current in common part of winding of auto transformer. Calculate current in common part. So here figures very important. First, what is the primary side voltage here? 800. Secondary voltage 600. Means primary should be 800 volts, secondary should be 600 volts. Then the figure will be in this way we get. This is 800 volts on primary, but secondary side we need only 600, so we need a tapping at 600 volts. So here let us take, this is 600 and it is supplying a load. That load resistance value is 6 ohms given, and how much voltage it is? 600 volt. Now we have 600 volt here, and what we need to find? Current in this common part, and for that we need this current I2, and let this is primary current I1. If you know I2, I1, then we can apply KCL and we can find the current in common part here. Now what is the current? Voltage is there, resistance is there, then current equal to 600 divided by 6, nothing but 100 amperes it is. Okay, secondary current. Then how to find primary current? If you know how much kVA it is delivering, kVA we take same on both sides, then I1 also we can find. The kVA output of transformer is voltage into current, 600 into 100, nothing but 60 kVA it is. 60 kVA. Then what is the primary current? Primary current equal to same kVA applied on both sides, 60K divided by 800. So we will get it is, calculate, it is coming 75 amperes. Okay, so this current 75, and this current we got already here, how much? 100 amperes. Then apply KCL at this point, 75 coming in this direction, but here going is 100 amperes. That's why how much current should come upward direction here? 25 amperes. But anyhow direction is not asking here, only magnitude of current in the common part. So what is the magnitude of current in the common part? 25. Okay, so the answer is 25 amperes for this. Clear, no? So in auto transformer topic, there is many times questions from kVA rating, means they will ask you kVA rating. So here kVA also covered, means with respect to given load kVA we can calculate like this. And current in common part, sometimes there is some questions in previous gate also based on this, even with the direction they asked, means they will give some points here, how the current 25 amps is passing, A to B or B to A, like that. Current direction is also important here. by applying KCL. 75 plus 25 total 100 amps it is. Okay, next question. See the question. This is on DC. A 6-pole lap connected DC generator having 5 volts per conductor. Okay. By rotating at a speed some n rpm not given. The flux per pole is 25 milliwebers. If the armature voltage is 240 volt, then its speed is dash. Okay, read again question and try to understand. So here speed not given, but voltage how much it is generating, that is everything given. So you can find easily, but think logically little bit. Conductors not given directly but given to you. Try to find out how much. Yes. Calculate this. Speed required. What is the speed the generator is rotating? Anybody? See, this is you can find out from EMF equation only. Eg is what Z phi n P by 60A. So using that only, but in that equation which is unknown for us directly means conductors, remaining everything available. Okay, so the equation Eg equals to Z phi n P by 60A. So here lap connection given, A equal to P gets cancelled, it is. Flux also given, voltage also given, but conductors not given directly. Then how can you find? Yes, easily we can find now. As it is lap connected, how many parallel paths will be there? Number of poles, that is 6. 6 parallel paths will be there. And the 240 volts indicates that is the voltage of one parallel path. All parallel paths same voltage will be there. Given that it is having 5 volt, generator having 5 volts per conductor. And what is the total voltage of one parallel path? 240. Then how many conductors in each parallel path? Number of conductors in each parallel path is equal to total voltage is what? 240, no? 240 divided by what is the voltage for one conductor? 5 volts it is. Now if you simplify this, we get 48 conductors. Check it is. Okay, 48 conductors per parallel path it is. But we need total conductors Z. Then how many parallel paths are there like this? Try to understand here. We have total 6 parallel paths like this. In the armature, there are 6 parallel paths total. And voltage of one parallel path is how much? 240 volts given. And voltage of one conductor is how much? One conductor 5 volts. Like this 240 volts total we are getting means then how many conductors are there in one parallel path? Like this 48 conductors are there in one parallel path. Then what is the total conductors? Z equal to 6 parallel paths, no? 6 into 48. Okay, substitute here. Now Eg is there, voltage 240 volt. Z is 6 into 48. Z value it is. Not given directly but given, should understand. Phi is 25 milliwebers, 0.025. Speed is unknown for us and poles are 6, anyhow that will be cancelled, 60 into 6. Okay. Now simplify, we get the speed of generator is around 2000 rpm. Cross check values, cross check it is. Okay. So the speed of generator is around 2000 rpm it is. So only important thing here is conductor calculation, not given directly but given. So one conductor voltage is 5 volts and total voltage given. Then you can find total how many conductors are there in one parallel path. Now we need total conductors in generator means number of parallel paths 6. So 6 into 48 taken. Clear? Next question. Next. See the question. Read this. A 220 volt separately excited DC motor running at 1400 rpm by drawing armature current or drawing a current of 14 ampere. Okay. The armature resistance is 0.4 ohm and brush drop is 2 volts here, total brush drop. If it drives a load of torque proportional to square root of the speed. So this is one of the important model where we are getting regularly questions in GATE, like load torque proportional to square of the speed or cubic of the speed. Okay, same model taken here. So now here I taken square root of the speed. Okay, no. Then the external resistance required in armature to operate the motor at 1240 rpm means initially how much speed it is, 1400. So when we add resistor in series with armature, definitely the speed of the motor reduces. Now how much resistance we have to add, external resistance, so that the speed of the motor is now 1240. From 1400 it will reduce to 1240 rpm. Okay, try this first. Try quickly on your own. Yes. Calculate. These problems are same procedure for every condition, square root of the speed or proportional to speed or square of the speed, anything. Okay. Calculate this. First, find out separately excited DC motor means flux not given here, flux constant it is. Okay. Then initial speed is N1 equal to 1400 rpm. Initial speed is 1400. And what is the back EMF in the initial condition? Calculate V minus IARA. What is the voltage? 220 minus how much current it is drawing? 14 amps into RA, armature resistance 0.4. But up to here don't stop, because there is a brush drop in this question. If brush drop also if you don't take, no, then small variation we get, definitely our speed whatever we will whatever the resistor value we get, it will not be within the range they mentioned. So this one should be taken, minus 2 volts brush drop. Now calculate the value of back EMF initially. So it is coming EB1 around 212.4 volts. This is EB1. This is initial case. Now we have to reduce the speed to what? N2 equal to 1240 rpm. Then we have to find new back EMF again here. Then when we get this speed after addition of external resistance, the current also will change. Current taken by motor also will change, because the condition here is it is driving a load torque proportional to square root of the speed. Load torque proportional to square root of the speed. But in separately excited motor, the electromagnetic torque proportional to what? Only current, no? Flux constant here. Shunt motor and this motor, flux constant. Then under steady state, if you equate IA2 divided by IA1, we get square root N2 divided by N1. So find out IA2 here, new current, how much it is? IA2 equal to, IA1 is 14 into root of N2 divided by N1. N2 means 1240. 1240 divided by EB1 1400. Simplify this, we get the value of IA2. How much it is? Yes, it is coming around 13.175 amperes. Okay, slightly decreases current. 13.175 under this condition. This is the new current. So once you have the new current, now you can find the back EMF with addition of resistance, which is unknown for us. Therefore, EB2 is equal to V minus 220 minus, what is the IA2? 13.175 into RA plus RE. We are adding some resistance now in series with that, 0.4 plus RE. Minus 2, don't forget this, brush drop is there. Then keep this equation as it is. Now therefore, according to speed relation, before addition and after addition of resistance, N2 by N1 we can write as EB2 by EB1 into phi1 by phi2 from back EMF, phi1 by phi2. Then N2 is there 1240, N1 also there 1400, which is equals to EB2 220 minus 13.175 into 0.4, simplify this, minus 13.175 RA divided by EB1 value is there, no? How much it is? 212.4 into phi1 by phi2, cancel it is. Okay, this is a separately excited motor means flux constant if nothing is mentioned about excitation. If excitation changes by 10% or something given, then we have to consider, otherwise no need, one it is. Now only unknown in this equation is RE. Simplify this, the value of RE will get. Tell me how much RE? Try to do quickly, simultaneously, and give your answers. What is the value of RE you are getting? Send your answers, everyone. RE value how much? Yes. Yes. So it is coming around, check 1.87 ohms. So if you add this much value of external resistance in series with the armature, the speed will be reduced to 1240, under which condition? The load torque proportional to square root of the speed. Suppose if they given some other condition, so here only proportional to n or n square, same procedure again you have to simplify and then calculate back EMF and then substitute here, we will get the value of RE it is. Okay. Right. Next question. See the next question. Completed? Next. See this question. Read the question first. Which of the following are correct during armature reaction in a DC motor, of a DC motor? Okay. So armature reaction takes place in DC motor. Then what happens? Which options is correct from the given? First option is the flux density decreases at a trailing pole tip. The flux density decreases at a trailing pole tip. So is it right or wrong? Should remember figures for this. Generally flux density increases at a trailing pole tip if it is a generator case. But if it is a motor, the flux density increases at leading pole tip and decreases at trailing pole tip. So the first one is the flux density decreases at trailing pole tip. So it is correct one. Next, the spark can be reduced by shifting the brushes in its opposite direction. So here you should keep in mind this one, motor. So if you want to reduce the spark or if you want to improve commutation, in which direction brushes should be shifted always? In the direction of generator, or we can say it in opposite direction of motor. Both are correct. In the direction of generator or opposite to motor. So this is motor they given. So the spark can be reduced by shifting the brushes in its opposite direction. Yes, opposite correct only. Next one. The polarity of interpole is opposite to main pole ahead to it. Tell me, this one is right or wrong? Third option is right or wrong? Try to answer. The polarity of interpole is opposite to main pole ahead to it. But actually we know if it is a motor case. So one statement we learn. What is that? The polarity of interpole is same as main pole, which is behind to the interpole. But here the polarity of interpole is opposite to main pole. See, same as main pole, behind. But with respect to opposite, if you want to say, then what is the statement? The polarity of interpole is opposite to main pole ahead. Opposite to main pole ahead. If you have confusion still, so go through once that armature reaction diagram, in that methods to improve commutation. So there you will get this one, how the interpoles we placed and how the polarity of interpoles we choose for generator and motor both. So here the polarity of interpole is opposite to main pole ahead. Actual statement what we know is the polarity of interpole is same as main pole, which is behind. Whatever behind is the same. But if it is ahead you want to say, then opposite you have to take. So this one also correct only. And fourth one, the flux density increases at trailing pole tip, decreases at trailing for motor, and the flux density increases at trailing. This is wrong. For motor it is. If it is given for generator, then this one is correct. If it is given for generator, this is correct. But motor it is asking. So which are correct here? A, B, C. These three are correct. A correct, B, C also correct. Okay. Next question. See the next question. See the question from induction motor. Try to answer. A 3-phase 4-pole 50 Hz squirrel cage induction motor having slip speed of 60 rpm. Slip speed of 60 rpm. Then which of the following are correct? Okay, first you read the statements on your own and try to guess which are correct. Given that first one, the motor is rotating at 1400 rpm. Second, the motor is rotating at 1440 rpm. Third, the rotor frequency is 120 oscillations per second. Okay, and fourth, the rotor copper loss is 4% of air gap power. So with the given data, some options are there. Now, which are correct out of this? Tell me first one is right or wrong. First of all, 4-pole 50 Hz induction motor. What is the synchronous speed? Immediately you should write 1500 rpm, 4-pole. Okay, 120 F by P, 1500 rpm it is. Now, squirrel cage induction motor having slip speed. Slip speed is nothing but relative speed between RMF and rotor, ns minus n. This value is given 60 it is, 60 rpm. Slip speed it is. Okay, then we have already ns value, then you can find the n also from this. Then what is the ns? 1500 minus n equal to 60. Then what is the speed of the motor? 1500 minus 60, 1440 rpm. So at what speed motor is rotating? 1440, not 1400. So this is wrong, this is correct. Motor is rotating at 1440 rpm. Now third one is check. The rotor frequency is 120 oscillations per second. What is the rotor frequency under running condition? The rotor frequency is nothing but slip frequency only, no? The rotor frequency is SF. And what is the value of S here? So S equal to ns minus n by ns. Ns minus n is 60 divided by ns is 1500 into 50. Now simplify this. You will get this is 50 into 1 0 here cancel, 1 0 here cancel. 5 3s, 3 2s, 2 Hz it is. 2 Hz, 2 cycles per second or 2 oscillations per second we can call this. This is what rotor frequency, 2 Hz. But they did not given in Hertz directly, oscillations given. So oscillations per second and cycles per second. So both are correct only. But 2 Hertz means what? Actually 2 cycles per second it is. 2 cycle per second, or we can call 2 oscillation per second. 2 oscillation per second. But this is 120 oscillations per minute here. Not second, check it is. Per minute should be there. Then if it is per minute, no? Per minute how many seconds we have? Per minute 60. Then per second 2. Then 60 into 2 is 120 oscillations per minute it is. Okay. But if you take per second, that will be wrong again. Okay, both here. If you take maybe per minute, will be there here. Suppose if it is per second, no, this is wrong statement. Okay, so right now take as it is, per second is there, no? As it is, choose it per second. Per minute if it is, then it is correct. But what is given here? Per second given, no? So 2 oscillations per second is correct, but 120 oscillations per second means wrong it is. Then fourth statement, rotor copper loss is 4% of air gap power. Is it right? Tell me. Rotor copper loss is 4% of air gap power. Is it correct? We have one relation, no? With respect to rotor copper loss and air gap power or rotor input power. What is that? Rotor copper loss divided by rotor input power, nothing but air gap power it is. Rotor input only we call air gap power. So what is that relation? Copper loss by rotor input? Yes, no? This is yes. Then what is the rotor copper loss? Slip times of rotor input power or air gap power. What is the slip here? Slip is how much? 60 divided by 1500 means you will get it is 4% only, means 0.04 into rotor input power, it is Pn. So in percentage they given, yes, it is 4% of that only, rotor input power. So this is also correct. The rotor copper loss is 4% of air gap power. Okay, but take care here, 120 oscillations per minute if given, this is right. But per second is there, no? That's why it is wrong, you can take. Now, which one correct here? This option B correct, option D correct, B and D. B and D for this. Okay. Next question. See this question. Try to read quickly and answer it. Read the question. A 3-phase 4-pole 50 Hz squirrel cage induction motor drawing a power of 12.5 kilowatt. So motor drawing a power of 12.5 kilowatt means what? That is stator input power, no? Yes, that is motor input directly. And when rotating at a rotor frequency of 4 Hertz, if the stator copper loss and core loss is 1.5 kilowatt and the rotational loss is 5% of air gap power, then the motor efficiency at this condition is dash. First try to do on your one and then cross check the answer. Do it quickly. So we need motor efficiency. What is motor efficiency? Motor output by motor input, no? So the motor efficiency is equal to motor output divided by motor input. Motor input is there, 12.5 kilowatt, but motor output is not there. Then how to find that motor output? What is the motor output means again? Is it net power or gross power? See, motor output is always net power because from the motors we take shaft output always, but not rotor output always. Okay, so motor output generally shaft. Then how to find shaft power? If you know the gross power, from the gross we will remove that mechanical loss. Then we can get shaft power. Like that, that is the net output or motor output. But in some of the questions, if there is no possibility of finding mechanical loss is not given, then we will take gross power itself approximately the output of motor directly. Okay, but right now, can we find means? Yes, because the rotational loss is 5% of air gap power. 5%, whatever that air gap power. First calculate air gap power. Air gap power means what? Rotor input power. What is the rotor input power always? The stator output of induction motor is nothing but rotor input power, which is called air gap power. Both are same, stator output. That is itself rotor input. Now what is the stator input power? 12.5 kilowatt. No? Therefore, the rotor input power, this is only air gap power, or stator output it is. How much? Stator input minus stator losses. Stator input is 12.5 kilowatt minus, what is the stator losses? Given stator copper loss and stator core loss combinedly, 1.5 kilowatt it is. Then 12.5 minus 1.5 is 11 kilowatt. This is the rotor input power or air gap power it is. Okay. Then which one required? If you want to find net mechanical power, gross required first. Gross. And how to find gross relation? We have one relation. Gross mechanical power to the rotor input power. What is that? 1 minus S. From here, find out the gross power equals to 1 minus S. What is the slip of the motor? It is having a rotor frequency of 4 Hertz, means SF equal to 4. Then what is the S value? 4 divided by 50. How much it is? Calculate slip 4 by 50. 0.08. Okay. 0.08 is the slip. Now substitute here. 0.08 into rotor input power. 11K it is. Then what is the gross mechanical power? Calculate. It is coming 10.12 kilowatt it is. 10.12. This is the gross power. But if you want to find motor efficiency, we need net power. This output is nothing but net. And that net we can find from gross if you know rotational loss. What is the rotational loss here? 5% of air gap. No? The mechanical loss or rotational loss total equals to 5%. 0.05 into rotor input. What is the rotor input? 11K. Okay, calculate how much it is mechanical loss. Calculate that, and then net mechanical power is equal to P gross minus mechanical loss. Gross power minus mechanical loss. What is the gross? 10.12 K minus this mechanical loss, whatever the value you will get, substitute here. 5% of that, no? Then it is coming net mechanical power, cross check it is 9570. Cross check every value, cross check from your end also. 9570. Okay, this is net power. But we need motor efficiency, no? Therefore, the motor efficiency now you can find the motor efficiency is equal to the output power to the input power. What is the output we got? 9570 watt. 9570 watt divided by 9570. 9570, and input power is stator input only, which is 12.5 kilowatt. 12.5 into 10 cube into 100. Then we get the percentage efficiency is, the motor efficiency, it is coming around 76.6 percentage. Okay. The efficiency at this condition. See the percentage efficiency, let us take it is in percentage how much it is. So it is 76.6 percentage. Okay. Next question. All of you got the same 76.6. Cross check the value. Right. Okay. See one more next question here. Okay. See this question from alternators. An alternator is to be synchronized with the bus bar using 3 lamps method. The lamps connected between RR dash, YY dash and BB dash. So L1, L2, L3 like that, L2, L3 you can take. So L1 connected between RR dash in the way, same way, YY dash, BB dash. And then if all 3 lamps showing equal bright and dark repeatedly, then which of the following are correct? Okay, first read this and you try to give the answers for this. See here, first option is both busbar and alternator have same frequency. See, first you should understand this statement here. The 3 lamps are showing equal bright and dark. Means bright also showing, dark also showing repeatedly, one after other. That means the lamps are flickering here. Lamps flickering means the 2 systems are not having same frequency. But what is the first one? Both busbar and alternator having same frequency. If they have same frequency, how the lamps we will get? Suppose they are having same frequency. Now you are getting dark. Then continuously dark only will be there. Bright you never get. Or suppose whenever we used to verify, at that time frequency matched and then you got some brightness there. Some brightness. Same brightness will continue and continuously. Means the brightness of lamp will not disturb if the frequencies are same. But when frequencies are different, then only we get alternatively equal bright dark means flickering of the lamp is possible. So this is not correct. Now second option C. Busbar frequency is less than alternator frequency. And third statement. Busbar frequency is greater than alternator frequency. Now, can you tell which one is correct out of this, or both are correct? Here, the lamps are showing bright dark, but I did not given any sequence of lamps here. Like first A, B, C sequence becoming in the same sequence it is dark, or A, C, B is dark. Like that I am not giving. Okay, then anything may be correct only. Second also may be correct. Busbar frequency is greater than alternator frequency. Or busbar frequency is less than alternator frequency. Both are possible. Here just lamps are becoming bright dark means flickering is there. But there is no condition that always this is greater, that's why it is coming. So both are possible here. Both are possible. Not any one. Okay, no? Next, both busbar and alternator having same phase sequence. This is right or wrong? Yes, 100% right only it is. Because if alternator phase sequence is same, then all the 3 lamps at a time dark, at a time bright. Otherwise, if phase sequences are different, you never get all 3 lamps same brightness and same darkness. Maybe 2 lamps equal bright, other lamp will be dark. So like that, there is a chance of different phase sequence. But phase sequence same means RYB, other, suppose all busbar sequence RYB. Alternator sequence also RYB. Then as phase sequences is same, then at a time all 3 lamps will have same brightness or same position, maybe bright or dark it is. But if they are not having same sequence, then definitely they never show the 3 lamps equal bright and dark. Okay, that's why this is also correct here. So B correct, C correct, D correct for this. B, C, D it is. Okay, so both busbar and alternator having same frequency is wrong here. Because if they have same frequency, no, you never get flickering of the lamps. Remember this. Next question. Okay, see this question. 11,000 volt, 1000 kVA star connected synchronous generator has synchronous reactance of 0.2 per unit. It is delivering full load at 0.866 lagging to the bus bar. So it is delivering full load at 0.866 lagging to bus bar. If the turbine input increase with the constant excitation till the power factor reaches 0.96, already how much it is operating? 0.86. It is operating. Now turbine input increase to increase the power factor to this much value. So whenever turbine input increase with constant excitation, then the current supplied by generator to the bus bar or grid. Okay, try to read 1 or 2 times again question. Whenever excitation constant, the EMF of generator or alternator is constant. So according to initial data, first we have to find EMF here. EMF induced, okay, of alternator, and that EMF will remain same again. Whatever the power factor you change to increase the different values of power factor, excitation constant means EMF is constant. So according to that condition, we will solve easily this. Okay, first try on your own. But important thing here in this question, the impedance per unit reactance given. Reactance is not given in ohms, but remaining this voltage rating, kVA rating, they are in units, but only that reactance is in per unit. So we should convert first that per unit reactance to unit value first. What is the formula for per unit impedance, or X per unit equal to X in ohm into MVA divided by kV whole square, kilovolt, voltage square, volt ampere rating by voltage square. In MVA, if you take here kV square it is. Okay. Now we need ohmic value here. Per unit value is given, but we need ohmic value. Then how to find ohms? Reactance in ohms equal to 0.2 per unit into, what is the MVA rating? 1000 K, nothing but 1 MVA. This is 0.2 X in ohms, no? Calculate X in ohms, cross multiply kV square divided by MVA it is. What is the kV in voltage? kV means 11 kV, 11 square divided by MVA. MVA means how much MVA it is? 1000 K, nothing but 1 MVA, no? 1 MVA. Then if you simplify, the reactance in ohms we are getting, cross check this. Calculate, it is coming around 24.2 ohms it is. Cross check all the values, 24.2. 24.2 per phase. Okay. Right. Next, see here question. Initially, the star connected synchronous generator has the reactance. It is delivering full load at 0.86 lagging to bus bar. Full load delivering. Full load means how to find the full load current? Calculate the full load current. First, IA full load equal to kVA rating by voltage. 1000 K, 1000 into 10 cube divided by 3 phase, no? Root 3 into line value 11 K, no? It is 11 K. 11 K. Calculate this one. Current IA equals to 1000 divided by 11 root 3. So 52.48 amperes. Okay, 52.48 or 52.5. 52.5 amps it is. This is the full load current, and which power factor? 0.866 lagging it is, 0.866 lag. Okay. Now, at this condition, calculate what is the EMF induced in alternator first. It is delivering, no? So, at that time, how much EMF is induced? What is the formula for EMF? E equals to square root V cos phi plus IARA whole square, V cos phi plus IARA whole square plus V sin phi as it is lagging plus IAXS whole square. So excess value we got, but RA is what? Negligible. Not given means neglect that. Then what is this? Substitute here all the data. So here 11 kV is the line voltage. 11 kV star. No? Then what is the phase voltage of that? 11 k by root 3. The phase voltage 11 k divided by root 3. We get 6350. Okay, volt. Substitute here 6350 into 0.866 plus IR is 0 whole square plus V sin phi 6350 sin phi is what? If cos phi is root 3 by 2, sin phi is 1 by 2. Cos 30 no? Root 3 by 2. Then sin 30 1 by 2 0.5 plus IA XS whole square. What is IA? 52.5 into XS is 24.2 square. Find out this EMF value. Calculate that. So it is coming around 7071.25. 7071.25 volt it is. Okay. So this is the EMF induced at this condition. Now as excitation constant, that EMF remain constant under this condition. Okay. And now the turbine input or mechanical input or steam input all are same. If it is increases till the power factor reaches 0.96, means at this power factor what is the current delivered by generator. Now same equation we use again. What is EMF even at that 0.96 lag also? Same EMF, 0.96 power factor, sin phi will change. At that time current IA unknown. So remaining parameter V will not change, XS will not change, only IA is unknown for us. Then, so as turbine input increase till the power factor reaches 0.96 lag, then what is EMF at that time also? EMF remain constant as excitation constant. What is that value? 7071.25. 7071.25 equal to square root V cos phi. What is the bus bar voltage? It remains same 6350. 6350 into cos phi is 0.96 now plus IARA whole square 0 it is plus V sin phi 6350 sin phi. If cos phi is 0.96, what is the sin phi value? Sin phi 0.28, cross check, plus IA unknown for us, XS is what? 24.2 it is, 24.2 whole square. Now simplify this, only unknown in this equation is what? Current. The current we are getting, simplify that, square on both sides. Square on both sides, the square root gets cancelled, and then simplify little bit to find that IA value. So current definitely increases here. Whenever keeping excitation constant, if you increase steam input or if you increase load on alternator, any case, currents definitely increase. Okay, how to cross check? Even you got some value here, which is current previous 52.5. Suppose you got some 46.5 here. Is it correct then? No, you should cross check again, because whenever steam input increase, definitely current should increase. Then only it is correct. So here it is coming current. Current is 74.6 amperes. Cross check the values everyone. Cross check this. This is the current supplied by generator to bus bar now. As excitation constant and turbine input or mechanical input increases, as mechanical input increase, definitely it will supply more current to the bus bar or grid, anything. 74.6 amperes. Previously 52.5, but now excitation constant means first we calculated EMF, no? Now same EMF now also we taken, EMF remain constant. Up to which power factor it reaches? 0.96. Accordingly sin phi value we got, sin phi calculator, cos phi 0.96, no? Cos phi 0.96 and sin phi calculate. First find the angle phi here, then apply sin, you will get 0.28 it is. 0.28. Okay, so this is the value of current we are getting. Next question. 74.6 amperes. 74.6. Next. So as it is star connected, no problem here. Phase current, line current, everything same only, no problem. Next question. See this question. A 12.5 kilowatt, this is 12.5 kilowatt, 4 pole, 50 hertz, 3 phase slip ring induction motor runs at 1460 rpm on full load with a rotor current per phase of 21 amperes, allowing 0.6 kilowatt for mechanical loss. 0.6 kilowatt for mechanical. Then what is the rotor resistance per phase here? Rotor resistance per phase. Do on your own and try to calculate this value. Do it. Try to solve everyone and tell me your answers. Rotor current per phase. How to find rotor current, rotor resistance per phase? Current given, resistance required. Then if you know rotor copper loss, is how much, from there we can find 3I square R it is. Current they given, only resistance will be unknown. Okay, try to find out this. Send your answers, how much you are getting. Rotor resistance. It is rotating at 1460, 4 pole 50, 1500, 1460 rpm with a rotor current per phase of 21 amps, allowing 0.6 kilowatt for mechanical loss. And this is what here net mechanical power it is. So net mechanical power is there. What is that? Always power rating is shaft or net output it is. So net mechanical power is nothing but 12.5 kilowatt. Then what is the gross power? P gross. Net plus mechanical loss, no? 12.5 plus mechanical loss is how much? 0.6 K. 0.6 K it is. Then 13.1 kilowatt. This is the gross power. Gross mechanical power. So once you know gross power, you can find, from there also you can find 3I square R2 into 1 by S minus 1 is the gross power equation. From there also you can find. Otherwise, you have to find rotor copper loss. What is the rotor copper loss? The rotor copper loss divided by gross mechanical power. What is the relation of this? S divided by 1 minus S. And for that S value required again. What is the slip? S equal to Ns minus N. 1500 at what speed it is rotating? 1460 divided by 1500. This is 40 divided by 1500. Calculate how much slip. So it is coming the slip value 0.0267. 0.0267 slip it is. Okay, substitute here. Then if you substitute, we get rotor copper loss. The copper loss equal to 0.0267. Calculation should not do mistakes again in the calculations inside. Take care of this. 1 by 1 minus S by 1 minus S. What is that? 1 minus 0.0267 into gross mechanical power. What is the gross? 13.1 kilowatt. Then if you simplify, we get rotor copper loss here is coming. Cross check this. 353.7 watts it is. This is our rotor copper loss. This is rotor copper loss. Now, we need rotor resistance. So, what is the copper loss formula actually with respect to equation? 3I square R, no? 3 phase it is, 3I2 square R2 it is. So, here current they given, how much current it is taking at this condition. Now, 353.7 equals to 3, what is the current? 21 square into resistance unknown for us, 3I square R. Then simplify that, we get the R2 value 0.267 ohms again. So here values will confuse you a little bit. Here also there is 0.0267 slip it is 2.6% and it is 0.267 ohms of resistance. Rotor resistance is 0.267 ohm. Okay. So when you add this much, if this is the resistance, we have this much rotor copper loss with the given current, rotor current 21 amperes. Clear? Without rotor copper loss calculation also you can do this, because gross power equation is there, no, 3I square R2 1 by S minus 1 directly. In that also R2 will be there. Direct also you can substitute. Anyway. Okay, next one more, last question. Let's see. See the question. See this question related to V by F control. The speed of three-phase induction motor of 400 volt 50 hertz is controlled by using V by F control, means variable voltage variable frequency control method. For 400 volt 50 hertz, the speed of induction motor is 960 rpm. For 400 volt 50 hertz, the speed of induction motor 960, but poles not given. So you have to consider poles here. How many poles? Then always induction motors rotates near to synchronous speeds. So for 6 pole case, what is the synchronous speed? 1000. So it is nearest nearest to that, no? That's why 960 rpm it is rotating, means the poles are 6 indirectly here. Poles fixed, poles will never change. Only voltage frequencies is changing in this method. What is the speed of motor when it is operated from 325 volts? Frequency not given, so you have to find what is the frequency accordingly, because V by F constant, V by F ratio constant, V by F variable voltage variable frequency technique is nothing but we have to keep V by F ratio constant. How much voltage is there initially? 400 volts, and frequency 50 hertz equals to, now how much voltage applied? 325 applied. That means how much frequency we need to apply? Calculate from this. We get the frequency, it is simplify, frequency is 40.625 hertz it is. This is the frequency, new voltage it is. Now at this voltage and frequency, what is the speed? So the first thing to solve this question, you should know one condition. Generally with constant load torque conditions we take all these speed control methods. In that what is the condition is, the product of V by F into Ns minus N equal to constant. The product of V by F and Ns minus N. Already V by F constant here. Then which one to be constant for having constant torque is Ns minus N. Then according to this relation, already V by F constant, they will cancel. Even if you substitute, V by F ratio will be cancelled. Ns1 minus N1 is equal to Ns2 minus N2 for this. And what is Ns1 means? 50 hertz. 50 hertz, 6 pole, 1000 rpm it is, minus what is the N1? It is rotating 960 rpm, no? 960. This is equal to Ns2. How to find this one? 120 new frequency, 120 F by P. Poles will not change. This is 120. What is the frequency? It is operating now 40.625. 40.625, whatever you will get, divided by poles 6, minus N2 unknown. At what speed now it rotates? At this new frequency and voltage. Calculate the answer. How much it is? N2, the speed of the motor. This synchronous speed you will get 812.5, check it is 812.5, and we need the speed of the motor N2 here. The speed of motor N2. Tell me how much? Anybody solve? Speed of motor N2. Yes. It is coming around 772.5. Cross check everyone. Is it same? 772.5 rpm it rotates. So this is the speed of motor. Now it is operating at this new voltage 325. Frequency not given. That frequency we calculated because V by F control, no? Constant V by F ratio always. Accordingly, the new frequency is 40.625 hertz it is. Clear? This is the speed of the motor, 772.5. See, in the range you will get 772 to 773. So 772 to 773, anything. You can take 772 also correct, 773 also correct. So some range will be given, no problem. Anything you can write, either 772 or 773, anyone. Okay. So these are some of the questions we have today from total electrical machines for numerical answer type and also MSQ type. Okay. So in the actual exam also, take care of these two model of questions mainly, because numerical answer type, what is the advantage of MCQ is at least some answer is visible there in the options. Whatever we are finding out, maybe something will be there near to that. Like that we can identify and we can guess. But in numerical answer type, you cannot guess anything. Whatever you are substituting finally, that is only the final answer. And while writing that answer, again cross check whether they are asking phase value or line value and which connection they are asking. All this try to check. And MSQ also. To answer MSQ, we need to have a little good conceptual knowledge to answer this type of MSQ question. So take care of them, no problem. You can easily get it if you concentrate little conceptually good. If you are good conceptually, you can easily answer such type of questions also. Okay. So all the best to everyone.